Hello everyone, hope everybody's doing well. Today we're going to talk about Chapter 8, which is RF transmitters. Um, we have 4 basic requirements of a transmitter. It must generate a carrier at the correct frequency. It must modulate the carrier in frequency, amplitude, or phase. And it must provide sufficient power, and it also must provide a matching network to the antenna. The matching network to the antenna is something we haven't really talked about yet, but we will today. Okay, it's a very important part of the transmitter system. Okay, so 4 basic requirements. Okay, so generate a carrier, correct frequency, modulate the carrier, which was what we've been talking about, and provide sufficient power, and must provide a matching network. Now, as far as generating a carrier, you know that it has to be accurate because of FCC regulations. So it's usually crystal controlled, or always is crystal controlled. As far as providing sufficient power, that also obviously depends on the application. For a regular broadcast station, it could be 50,000 watts. For a citizens band or family band radio, it's between 100 milliwatts and 5 watts. For a VHF radio, it could be 10, 15 watts. For near field like Bluetooth, things like that, it's in the low milliwatts. So it all depends on the particular application. Okay. There's a couple of different transmitter configurations: high level, low level, and of course there's SSB. So this is a diagram of high level transmitter. The difference, or the distinguishing feature of a high level transmitter, is this part right here, where the final power amplifier, that's where the modulation occurs. Okay, so I have a microphone going into a little audio amplifier, a little preamp, okay, some speech processing, and what that does is it actually performs that dynamic range compression, maybe a little compression, so you don't overmodulate the modulation amplifier here, okay, and cause distortion. All right, so AM transmitters are normally high level, and you know what happens when you overmodulate AM waveform, right? You get that, we saw that in our first lab, you get that distortion. All right, so here's a carrier oscillator. No, it's crystal controlled. So that final power amplifier is the part where the modulation occurs. It doesn't occur over here. All right. The low-level transmitter, however, is usually used with FM, okay, and the same speech processing happens, but it actually causes modulation of phase. So we're doing indirect FM here. So phase modulation, we're doing indirect FM. Carrier oscillator adjusts the phase. So it's constant frequency, all right, but it's wiggling the phase back and forth, which results in indirect FM. And we have these frequency multipliers. We'll talk a little bit about how, we've already talked about how to do frequency multiplication. We'll talk a little bit more. And then the final power amplifier, okay, is usually a Class C amplifier, and it doesn't have any direct modulation to it. All the modulation is done up front. Okay. Then we have an SSB transmitter. Okay. Couple of different things here. Now we already did talk about how a balanced modulator generates what? It generates a double sideband signal. DSB is right here, double sideband. Then we filter out everything except for one of the sidebands, and then it goes into this mixer. Now, in a couple of weeks, okay, 2 or 3 weeks, we're going to talk about this process called super heterodyning, where you can take 2 signals into a mixer, all right, and actually cause an output which is a higher frequency than either of the inputs. So that's what's going on here. So I'm not going to get in too much detail about that, but you get at least 4 frequencies here. And this tuned circuit, what is that? That's a tank circuit. That is a bandpass circuit, and it only band passes the one sideband. All right, so you get the final linear power amplifier here that is only amplifying the one sideband because of this filter. Okay, this mixer here with this thing called, this is a local oscillator. That's what LO stands for. And again, in a couple of weeks, we're going to talk about this process. So don't worry about that too much right now. But just be aware that an SSB transmitter has this balance modulator and a sideband filter. You have to get DSB first and then filter everything out. All right? Now, today's modern digital transmitters obviously use DSBs. Okay, they use a lot of digital signal processing, and they form in-phase and quadrature waves. They're being sent to digital to analog converters, and they're mixed and summed. Again, this is the same process that we've talked about with the super heterodyning. And again, don't worry about the super heterodyning. That's more in receivers, but the process obviously is being used here for transmitters too. And those two in-phase and quadratures are summed together to a power amplifier. All right, in the modern world. All right. Okay, carrier oscillators. They're crystal controlled. They have to be. Why? Because they're required by the FCC. They're temperature and time stable. What do I mean about time stable? Well, over time, okay, let's say the temperature remains constant forever, right? Over time, components age. You know, we all do, but components age, especially capacitors. Inductors do too. Their insulation starts to break down, okay? But in particular, capacitors do. Right? The dielectric starts to break down, things like that. And they change in value, all right? Crystals don't really have that problem. They're made of quartz, very stable material, and so they're pretty much okay for a long, long, long time. So that's another good thing about crystal oscillators. Sometimes if you need super accurate frequencies, all right, you can use this thing called a TCXO, which is a temperature controlled crystal oscillator. And I believe I described this before, where you have basically a crystal oscillator with a little oven in it. The part has a little oven. It elevates the temperature in there, in the part, to something above ambient. And there's a thermostat in there that keeps it at that temperature. So if it gets a little warmer in the room, the thermostat detects that and turns off the heat. If it gets a little colder, it detects that and turns on the heat, keeps the crystal at a relative stable temperature, okay? Same temperature. So that really creates some very accurate frequencies. And how are crystals measured? How is the accuracy determined? Well, it's in an expression called parts per million, all right? And the way I like to most often describe this is that parts per million is like 1 part per million would be 1 hertz out of 1 megahertz, or 10 parts per million would be 10 hertz out of 1 megahertz. Okay, so you can scale that up or down any way you want. And the way you do it is with this formula here. Okay, so this is the center frequency F. You multiply times the parts per million and divide it by 1,000,000, and that's how much the frequency can vary. All right, so I think I have an example here. Yeah, so 16 megahertz crystal of 200 parts per million, which is very common. Okay, that's a pretty standard crystal. You can get them in 100 parts per million or 50 or whatever, but 200 that's a cheap one. That's pretty good. I mean, that's pretty good price for those. You don't really need that much accuracy. Ethernet crystals that run Ethernet systems and so on, networks, they're usually 50 parts per million. All right. This crystal here is more likely something used in a microprocessor. All right, it's standard 200 parts per million. But how much can the frequency vary? Okay, well, 200 hertz for every 1 megahertz. All right, so 200 times 16 is 3,200 hertz. Right, makes sense. So the possible frequency range is 16 million minus 3,200, which is 15,996,800. or 16 million plus 3,200, which is 16,3200, okay? And you can do it as a percentage if you want. Oops, 3,200 divided by 16 million times 100 is 0.02%, all right? We talked about the phase lock loop, I believe, last week. So this is an M over N divider. Actually, it's just the N. So this is a frequency multiplier. So coming out of your VCO, right, go into your frequency divider, and you get, if you have a 1 megahertz output, just divided by 10, this is 100 kilohertz. 100 kilohertz coming in from your oscillator reference. It basically multiplies this 100 kilohertz by 10 because of this, and you get a megahertz on the output. All right, remember that phase detector does everything it possibly can to command the VCO to generate a frequency so that this loop coming back here matches the input. Okay, and since we're dividing it by 10, it has to command the VCO to go 10 times faster or 10 times higher frequency in order to create the 100 kilohertz here. So this PLL frequency synthesizer is very common for generating frequencies in both variable frequency transmitters and certainly in receivers to tune a station, for example. Okay, this is a very clever frequency synthesizer circuit. Let me describe it to you. It's called direct digital synthesis, okay? And basically we have a microprocessor coming in here, all right? And this is an adder, all right? And we have a value that this microprocessor is putting into the adder, all right? So it keeps adding the same number over and over again, and this output feeds an address register. And the address register is connected to a ROM lookup table. And the ROM lookup table has digital values in it which represent a sine wave, okay? These are sine wave values, so digital representations of a sine wave. So as you go through the addresses, you go from, let's say it's a 64K register, so you go from 0 to 65,535, and then it wraps around again. Okay, that's how many addresses are in the thing. So when it wraps around again, okay, that could be the beginning of the sine wave. All right. Now the key is the faster you operate this address, you increment this address register, the faster you increment it. All right, the faster you're going to get through the ROM table, which means, and when it goes through this digital to analog converter, the higher the frequency of the sine wave is going to occur. Okay, so if you cycle through all of these addresses, let's say there's one complete sine wave in this ROM table. So all the values of a sine wave are digitized from, and let's say it's 64K, so 0 to 65,535. Okay, that's how many values are in here. Those are all values of one sine wave. So if we go through that sine wave in 1 millisecond, okay, that means you're going to get, what's 1 over 1 millisecond? Well, it's a kilohertz. You're going to get 1 kilohertz sine wave coming out, all right? Now, if you change the value of this constant so it adds quicker, okay, the adder goes quicker, what happens is you're going to go through the ROM table faster. And therefore, your sine wave is going to increase in frequency, okay? So here's a little formula here, okay? You can also change the frequency of the clock, all right? If your microprocessor is in control of that. So either one of those will do it. Change the frequency of the clock or change this constant so that the adder is adding more value to its result every clock cycle, all right? So this is a very clever circuit, direct digital synthesis. The other way this is used is something called adaptive predistortion. And if your sine wave coming out here is feeding an antenna system, all right? And that antenna system, that transmitter, okay, coming out of the antenna, that sine wave is distorted because of whatever. Let's say the transmitter is not linear, or the antenna has some characteristics that create some nonlinearities in the sine wave. What you can do is pre-distort the sine wave in the ROM table. In other words, don't make it a pure sine wave, but you can make it in such a way where it compensates for the distortion over here and fixes it, okay? Basically, you run a broken sine wave through here, and when it goes through the transmitter and the antenna system, the way that breaks that sine wave will actually fix it, okay? So if you have a bump here and a dip here, it comes out completely straight, a completely pure sine wave. So that's called pre-distortion, all right? And it can be adaptive pre-distortion, where at different frequencies, the antenna and transmitter system actually distort the wave differently. And so the microprocessor can know that and load the ROM table, and in which case it would be a RAM table, random access memory, and change it differently and load it as necessary. And that would be adaptive pre-distortion. Okay, should be a little bit of a review for you, power amplifier classifications. We looked at this in semiconductors. Okay, the Class A output, Class A power amplifier uses one transistor, okay, and that output transistor is constantly conducting, all right? It's going somewhere between saturation and cutoff. It's very inefficient because that transmitter is always conducting. In other words, if you put 0 volts in, no signal, the transmitter is still conducting. It's in the center of its operating range. All right, so it's getting hot. It's low distortion though. Okay, it's one of the lower distortion types of power amplifiers. So they're still used in situations where you need the minimum amount of distortion. They would not, however, be used for a high power application. And Class A is never used for high power. All right, now we have Class B, which maybe if you remember, there's 2 transistors, okay? One handles the top half of the sine wave, the other the bottom half of the sine wave. So each one handles 180 degrees. Now, when there's 0 signal input, all right, both transistors are off. So therefore, it's more efficient, okay? The problem is that there's a little dead band, because each transistor has to have, 0.6 volts or so to turn on. So between plus 0.6 volts and between plus 0.6 volts and minus 0.6 volts, you don't get any output. And that's a problem. So they invented Class AB, which is the same system, except we add diodes there on the input, which bias the transistors almost on. So it's just so that if you get the littlest amount of signal, those transistors turn on. So crossover distortion, I say it's removed here. It's almost removed. It's very minimal if it's done right, okay? And those diodes, the transistors, everything's matched. It's all on the same substrate, so everything's matched. So all the voltages, or turn-on voltages and so on, are the same, okay? And then Class C, which we talked a lot about in here, only conducts at the peaks of the waveform. It's very efficient because the transistors all the way on or all the way off. All right. Now, you cannot do amplitude modulation with this very easily. You can do FM. And as a matter of fact, when you put the Class C output, which is basically just peaks, little square, not really square wave, but little pulses, you can put it through a filter, and our friend Fourier fixes everything for us. It takes all those harmonics out of the peak of the pulse and creates your sine wave again. All right, and that's a very efficient way, and that is the most common broadcast transmitter type is a Class C. Okay, there's also this thing called Class G, which we don't really talk about here, but that basically has some inputs to the power supply, which gives it a little extra boost at certain times whenever peak power load, okay? There's class D, which is a switching type of power amp, uses pulse width modulation, which again we've talked about, and it really uses a capacitor on the end that gets charged as a charge pump and will reproduce the input signal as a series of pulse width modulated pulses, and those are put through a filter which recreates the input signal. Very common for audio applications now. Pretty much every audio amp, your stereo, your iPhone, everything is a class D type amp, okay? Okay, the last topic I think for today is impedance matching networks. Now, it turns out that a transmitter output and an antenna, the impedance are very seldom matched, okay? And they have to be the same in order for there to be maximum power transmitted out the antenna. If not, what happens is you get this thing called the voltage standing wave ratio, or voltage standing wave, which is the voltage, some of the voltage gets sent back, gets reflected off out of the antenna, and it gets sent back into the transmitter, which wastes that power. That power never comes out of the antenna, okay? In fact, it can damage the transmitter if it's bad enough. So we always have to match our antenna to the transmitter in impedance, okay? And we use matching networks to do that. So here's one that is not matched, okay? So here's the load of the, this is the antenna, okay? This would be this impedance here, and this is the transmitter output impedance. And we're assuming that these do not match. So this could be you know, 20 ohms, and this could be 50 ohms. All right, they're not equal, so there's a problem. All right, so what we do is we put this impedance matching network in between the two, which fixes it. Okay, and there's several different types. Okay, there's the three we're going to talk about. We're going to talk about a couple more, but the basic ones are L networks, T networks, and pi networks. And the reason they're called L, T, and pi is because that's what they look like. They're made out of capacitors and inductors, and they're arranged in circuit arrangements that look like these three things, an L, a T, and a pi, and I'll show you here. These are L networks, except for this one. All right, the textbook has this in there. This is actually a T network. See the T, a capacitor down here, and two inductors. But this is an L network. This figure A here, it's got a capacitor and an inductor. All right, this one has an inductor followed by a capacitor. All right, and this one has a capacitor followed by an inductor coming down like that. But this indeed is a T network. But you arrange these in these different circuit arrangements depending on whether the load is less than the source or greater than the source. There's two different scenarios here. Okay. There's formulas associated with these. We present the L network design equations here. We also do an LCC later on. But these are the design equations for that. I think there's some examples in the text. And I think we do an example here too for an LCC. But basically, you're calculating the inductive reactance here of your inductor. Here's your Q. Here's your capacitive reactance. This is for a situation where the load resistance, okay, or inductance is less than the transmitter or output resistance or inductance or impedance, okay? But the situation where the load impedance is greater than the transmitter impedance, we use these formulas. They're the same with the exception of this. This is reversed, okay? This has, I know it's a little hard to see. I'm going to post this PPT PowerPoint on our Canvas site, so you can take a closer look at it. But this is Ri over RL in this Q equation. This equation has RL over Ri. Other than that, they're the same. Okay. Okay. Here's a this is a pi network. See how it looks like a pi? Kinda. C, L, C. And then here's a T network. Another T network. Two L's and a C. Looks like a T, right? Now the Q has a little bit better control over these, over as opposed to an L network. So that's an advantage. That's why you would use that instead. There's some variations in bandwidth and things like that. All right, let's see. Okay, so this is a type of a T network, an LCC network. All right, and there's a design procedure for here. You select the Q, calculate the inductive reactance, calculate the capacitive reactance of this capacitor, C1. Then you calculate the capacitive reactance of that capacitor. I'm sorry, C2. I guess these are backwards, but you do C2 first and then C1. And then you compute the final L and C values. All right. So I think I do an example here. Yeah. Okay. So C2 is calculated. So first, select the desired Q. So I'm going to say Q is 10. All right. This example is in the textbook. The load impedance is 50 ohms. And the frequency is 155 megahertz. So we're going to say calculate the Q. Calculate the inductive reactance, XL Q times R load, or RI, which is the input impedance, okay, which is 6 ohms. I think I forgot to put that there. 6 ohms is our RI, so that's going to be 60 ohms as our inductive reactance. The inductive value is XL divided by 2 pi F, so it's 51.4 nanohenries. Then we calculate C2. All right, so C2 is this formula here. Again, these are backwards. This should say XC2 and that should say XC1. So XC2 is this expression here. We get 166.73 ohms. Calculating the capacitor value, it's 1 over 2 pi FXC, and you get 6.16 picofarad. And then lastly, calculate C1, and doing the same process with this formula over here, and you get 11 picofarad. All right, so there's a little example for an LCC network. Now, we were going to do a lab on this. It was going to be a multi-sim lab. The multi-sim program doesn't work very well for this, unfortunately. We don't get accurate results, so it's almost just as well we're not doing it, so don't worry too much about that. Okay, the other type of matching is systems uses transformers and balance. Now you can actually use a transformer to match impedances, okay? And the turns ratio determines the impedance ratio, okay? So the output impedance of the source, which is Zi, okay? And here's ZL, which is the load impedance, okay? You can establish a relationship between those using the turns ratio, primary over secondary squared. So if you want to match the two, okay, so you want to match this output impedance to the load impedance, all you do is set up a transformer, right, with a turns ratio that matches the square root of the quotient of Zi divided by ZL, all right? And this is done quite often, most often used in cable TV systems, so the little transformers outside your house on your that split your cable into different rooms and so on. You can use, this is what's going on there. Usually there's more taps on here. There's two or three secondaries. So if you have a primary and then three secondaries, that's a three-way splitter. this formula is used for that. Okay, this is most likely 75 ohms on the input. And then we have balance. Balance stands for balanced, unbalanced. Okay, and they're used to match balanced sources to unbalanced sources. So balanced and vice versa. So balanced loads to unbalanced sources, and balanced sources to unbalanced loads, and so on. The balanced source has two outputs, right? It doesn't really have a ground, right? Both sides are moving. That defines a balanced output. You have a plus and a minus, right? Unbalanced has a signal hot, if you will, and ground, right? So it's unbalanced. So unbalanced, an example of an unbalanced interface would be your cable TV cable or one of the RCA jacks on your stereo. It has an outside shield and an inner conductor. So this would be the outside shield, and that's the inner conductor, right? Balanced, however, doesn't have a ground. It has two signals that are operating differentially. So that would be perhaps a microphone signal, a balanced microphone signal, which has plus and minus. Or an Ethernet cable. Ethernet cables have 4 conductors, typically plus and minus, all right? So it's an example of a balanced interface. But if you want to connect one to the other, the best way to do that is using a balun. And this is a balun. This one is matching a balanced input to an unbalanced load, okay? Now you can also match a unbalanced output of something to a balanced load. Okay, so it works either way. All right, baluns are often used again in audio systems and in RF systems to match balanced to unbalanced. Okay, and then lastly, I just wanted to say that we're going to have an exam on April 7th. I have next week here because it's already the beginning of this week. April 1st, I believe, is coming up in the middle of this week, and April 7th will be the following week. So you have a week and a half to study for this thing. It's on chapters 5, 6, and 8. It will be open book and open notes. Okay, so you can look at your material. It's going to be the same format as the midterm number 1 we took in class. Okay. Fill in true, false, short essay, solve the problem. Do all the text examples. Just do them on paper, all right? That'll help you. It's going to be a timed exam, so you're not going to really want to spend a whole lot of time searching through the material trying to find the right answer. You can do that, and I hope you can. I want you to. But you're going to run out of time if you have not looked at the material closely. So please study for this, all right? And finally, most importantly, stay safe and healthy, and keep washing those hands. Take care.